chapter 14, which is trig functions, simplifying and solving them algebraically as opposed to with so many pictures of triangles and circles. Here's actually our unit circle from before. This point right here is the point 0.6, comma 0.8. And I know that the radius of this circle is 1. It's a unit circle. If I think about the triangle that comes from it, this is 0.8, this is 0.6, and we know that 0.8 squared plus 0.6 squared would have to equal 1 squared by the Pythagorean theorem. So 0.64 plus 0.36 does in fact equal 1. But we also know that the x values are cosines and the y values are sines. So x is really sine of theta, x is cosine and y is sine. So y squared plus x squared is the same as sine squared plus cosine squared. Whatever your angle theta is, doesn't matter which point I picked along this circle, sine squared plus cosine squared equals 1. That is called an identity. It's actually called a Pythag identity, and there are 3 of them. And we use and play with identities in this chapter to simplify and solve trig equations. The 3 basic identities you already know is cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent, which is cosine over sine. Having those 3 memorized makes these chapters go much easier. Here's 3 new ones. We just talked about how sine squared plus cosine squared is 1. You can manipulate those 2 to give you tan squared plus 1 is secant squared, or cotan squared plus 1 is cosecant squared. And sine squared, when you see this, literally just means sine of theta times sine of theta. We don't tend to say the theta. It is sine squared theta, but I just say sine squared and cosine squared. So we simplify some problems. Simplifying is very weird at first. It's tough because you don't know where you're supposed to end or where you're going all the time, but a good idea is to always take tangent and cotangent and write them as sines and cosines. So tangent is sine over cosine. So we have this. Well, this cosine on top cancels with this cosine on the bottom. So we're left with 1 minus sine squared, because these 2 sines right here combine. Since we have 1 minus sine squared, well, that's pretty similar to this identity up here. In fact, if I take this and subtract a sine squared from both sides, I know that cosine squared is really 1 minus sine squared. So this 1 minus sine squared here just becomes a cosine squared of theta. And now it's simplified. We took it and wrote it in the simplest trig form we could, which hopefully involves just like 1 sine or cosine or tangent. Sometimes it can involve 2, or things more complicated. But this is at least a simpler form than the original problem. I'll do the next problem on the right. Tangent is sine over cosine. Cosecant is 1 over sine. The sine on top cancels the sine on the bottom, and you get 1 over cosine, which is secant. So it simplifies to the secant of theta. Here I have sine theta times cosine theta, and cotangent is really cosine over sine. I know tangent is sine over cosine, so cotangent is cosine over sine. The sine here cancels this sine here, and this is just cosine squared. This is pretty basic and pretty intro. You're just taking sines and cosines out of tangents, and every once in a while finding a Pythag thing somewhere. They'll get a bit more complicated. This isn't much more complicated, but 1 plus tan squared, right here, cosine theta times 1 plus tan squared. I know that 1 plus tan squared equals secant squared. I'll go split screen. So, this is the same as cosine theta times secant squared. That secant squared, I know, is 1 over cosine squared. So this 1 cosine on top cancels with 1 of these cosines on the bottom, and you end up with 1 over cosine, which is secant. Now this problem on the right has addition of fractions And whenever you're adding fractions, you want a common denominator. Well, the common denominator is sine cosine. So I'm going to do this times sine on top and bottom, and this times cosine on top and bottom. That gives me sine squared over sine cosine plus cosine squared over sine cosine. And I know that sine squared plus cosine squared is 1. So because I have a common denominator, I can now add up these fractions. So I have sine squared and cosine squared over sine cosine. Sine squared and cosine squared is 1, so it's 1 over sine cosine. But 1 over sine is cosecant, and 1 over cosine is secant. So it's cosecant theta, secant theta. And this one's a bit less gratifying because you don't end up with just one trig function, you actually have 2 of them. I'll write that better. Cosecant theta, secant theta. But that's okay. It's still simpler than what we started with. Just a couple more. In your book, here's some strategies. Always look for a Pythagorean identity whenever you can. Put everything in terms of sines and cosines when you can. And after you've done those 2 things, there's just a few things you try, like getting common denominators, or factoring, or substituting things that are equal for other things. You kind of just have to sort of guess and play around with stuff to try and make this work. In your book, there's a few more identities that I'm not going to put on the screen right now, but one of them says that the sine of pi over 2 minus theta is really cosine theta. And one also says the cosine of negative theta is really just cosine theta. Another identity, cosine of pi over 2 minus theta is really sine theta. And sine of negative theta is negative sine theta. And you probably don't really follow that at all. This just seems like I'm pulling things out of nowhere. But like I said, these are all identities you can find in your book, where this right here is actually equal to this. And this right here is actually equal to this. And we can talk about later why that's the way that it is. In fact, maybe we'll do that at the end if you'd like to. I don't know why I'm asking if you'd like to, because you're not actually here responding to me. But cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. And we know that cosine squared plus sine squared is 1. So that all simplifies down to just 1. So those are your examples of basic trig identities. Sure, why don't I discuss why they're the way they are? That might be worthwhile. One identity is the cosine of pi over 2 minus theta equals sine of theta. What we talked about in class, how cosine means literally the complement of sine. Complement meaning they add up to 90 degrees. Well, pi over 2 is the same as 90 degrees. The way you find a complement is you do 90 minus the angle, and that gives you the complement. So when you do the cosine of pi over 2 minus theta, you're really finding the complement of that angle, and the complement of that angle gives you sine. So the cosine of pi over 2 minus theta comes out to sine. And same with sine. If you do the sine of pi over 2 minus theta, you get cosine because you're finding complements. Another identity that we have is that the sine of negative theta equals negative sine theta, and the cosine of negative theta is just cosine of theta. People get confused by this one at first, but it's actually quite simple. I'm going to draw an x and y axis here, and I'll put a unit circle on it. So we'll pretend like this circle has a radius of 1. If I travel theta degrees, and let's say theta degrees puts me right here. This is theta degrees. Well, there's going to be a cosine and a sine, and that's x and y. Cosine is your x, sine is your y. If I travel negative theta degrees, I just take that and I do the opposite direction. That would put me here, traveling negative theta degrees. Well, the cosine value is going to be the same. The x-coordinate doesn't change. The y-coordinate is the one that flips. The cosine value doesn't change. Whatever it was before, it stays. So in this case, it's like negative, we'll say root 3 over 2 or something. Well, here it's still negative root 3 over 2. But the sine value, which was a half, now flips, become negative a half. So the sine value, a negative angle, flips the whole entire y value, but a negative angle doesn't change the x value. That's all that's saying. So you might find that helpful, might not, but there it is.